Hello, engineers and curious minds. Welcome back to our channel. My name is Sia Siew Wei. In this video, we are going to dive deep into the fascinating world of CMOS technology. In this sharing session, we will be sharing a brief introduction to CMOS, its 3D structure, explanation of each layer, and last but not least, explanation of CMOS fabrication process. Now you may wonder how NMOS and PMOS transistor combines to become a CMOS. Simply connect the transistor like this. You may ask, what is the advantage of this? Its key benefit is about low power consumption, where based on its concept of complementary working, when one is on, another one is off. Now, let's insert some essential voltages. And let's see how this connection in actual implementation. Here it is. This diagram shows the top view of schematic diagram of 20 to 10 PMOS to NMOS inverter. From this 3D structure I shown, it will be 3-type structure, but in the later session, N-type CMOS structure will be discussed extensively. It employs two separate types or wells within the silicon substrate to create the P-channel, PMOS, and N-channel, NMOS transistor in a complementary way. You may wonder what are these different color structure means. First, blue color represents metal layer mask. For your information, CMOS involve both vertical and horizontal integration. Connections are established vertically lead down to the substrate, while metal interconnect layers facilitate horizontal connections. Metal interconnect layers run above the silicon substrate and is used to connect various components on the chip. These metal layers are responsible for routing signals, connecting the source and drain region of transistor to other components, and facilitates the communication between different parts of integrated circuit. Second, pink color representing the connection of gate mask. It is the mask consists of gate terminals, polysilicon, as well as a layer of gate oxide. The gate structure of NMOS and PMOS are typically aligned in a way that they occupy the same physical space. Third one will be green color mask called active layer mask. This mask defines the active layer of the transistor, including the location of the transistor gate, source, drain areas. Followed by the gray color mask representing the substrate. Next, black color mask known as the contact mask is used to establish the electrical connections between different layers in an IC, facilitating the routing of signals via metal mask. Last but not least, yellow color mask known as a rail mask. Now, let's look deeper into what is inside this mask. It starts with the creation of two separated regions within the silicon substrate, which is the M well, another one will be P well. It encompasses the terminals such as drain, source, gate, and bogey of those terminals. And those terminals are heavily doped N+ and P+ area.
Thank you, Eric. Now let us discuss about layers in CMOS IC design. In IC design, signals and power need to be transferred from one part of the chip to another, more specifically from one device to another, such as a transistor. As modern-day chips can contain trillions of transistors, routing all these devices correctly and efficiently is very challenging as the space available is limited. This causes congestion issues, where the wires do not have enough space to be placed. Metal layers help alleviate some of these problems by giving the ability for the routing to take place in 3D space. These layers specify the level at which the metal lines can be placed, The metal lines at each layer are connected to the upper and lower layers by structures known as vias, which acts as the bridge between wires on two layers. The number of metal layers depends on the foundry and the technology node used. For example, 7nm TSMC technology node uses 14 metal layers, or 7nm Samsung technology node uses 30 metal layers. As we go higher up the metal layer stack, we notice that the width of the metal line increases. This is to reduce resistance and allow more current to flow for larger power distribution and improve signal propagation. The highest metal layer will connect with the I/O pads or bumps, which acts as the I/O pins connecting the internal devices with the outside world. Another important point to note is the metal layers are drawn such that it alternates in direction. For example, the lines on metals on M0 are drawn horizontal, M1 lines are drawn vertical, and so on. This is to make sure metal layer routes are kept away from each other to avoid congestion and to reduce crosstalk. Crosstalk is the unwanted coupling of signals between adjacent wires located very close to each other, which can be represented as a parasitic capacitor connecting the two wires. When the aggressor line changes voltage, the mutual capacitor causes the voltage in the victim line to also change. This can cause glitches and delays, creating switching errors and affecting performance. When 2 points require a connection, the routing tool identifies the shortest path and employs the minimum number of layers necessary to achieve desired routing objectives. When the metal layers are utilized optimally for routing, it can ensure efficient signal transmission and enhance the overall performance of the design.
Alright, let's dive into the world of CMOS fabrication. First up, we start with choosing our foundation, which is the substrate. For the annual method, we go with a P-type silicon substrate. It's like the canvas for our circuit artwork. Next is oxidation. Now, we need a protective layer to shield our substrate from contamination. We create that using silicon dioxide. It's a bit like putting up a barrier. We heat things up in an oxidation chamber, exposing the substrate to oxygen and hydrogen to create a silicon oxide layer. Next is step 3, which is growing of photoresist. Next, we are going to use a photosensitive emulsion in a process called photolithography. It's like applying a special film to our wafer to allow for selective etching. Step 4 is masking. Now, let's get creative. We use a stencil mask to create a specific pattern on our photoresist. Think of it like a projecting light through a stencil to make a cool design. This light exposure hardens the photoresist in the exposed area. Next is step 5, removal of unexposed photoresist. Time to reveal our pattern. We remove the mask and wash away the unexposed photoresist using a special chemical. It's like developing a photograph. For step 6, which is etching, the silicon oxide barrier is next. We immerse the wafer in an etching solution with hydrofluoric acid. This removes the silicon oxide from the areas where we want to introduce dopants, which are the impurities. For step 7, it's the removal of whole photoresist layer. The photoresist mask is no longer needed. We strip it away using a chemical solvent, much like peeling off a sticker. For step 8, this is where the formation of N-well occurs. Now we are ready for some action. We introduce N-type impurities into the P-type substrate through the exposed region. This creates N-well regions in our silicon. Step 9 is the removal of silicon oxide. The silicon oxide layer has served its purpose and it's removed using hydrofluoric acid, revealing the N-well regions. The deposition of polysilicon will be step number 10. To avoid issues with gate alignment, we deposit a layer of polysilicon over a thin layer of gate oxide. This polysilicon layer can handle high temperatures during subsequent steps. For step 11, which is the formation of gate region, we only want the polysilicon where our gates will be, so we remove the excess, leaving behind just the necessary areas for NMOS and PMOS gate formation. For oxidation process, step 12, we add another layer of oxidation, acting like a protective shield for the steps to come. For step number 13, which is masking and diffusion, now we get into defining regions for the diffusion of N-type purities. These regions will become the terminal for NMOS transistors. For step 14, which is the removal of oxide, the oxide layer is stripped away. revealing the regions for diffusion and metallization. Step 15 is where the p-type diffusion occurs. Just like the n-type diffusion, we introduce p-type impurities to create the terminals for PMOS transistors. For step number 16, laying of thick film oxide. This is where, before we get to the metal terminals, we add a thick film oxide layer to protect areas where no terminal is needed. Whereas for step number 17 and 18, this is where two processes occur at the same time, which is metallization and removal of excess metal. Time to connect the dots. We lay down metal terminals, typically using aluminium, to create interconnection. We don't need all the extra metal. It's like trimming the edges. We remove the excess metal from the wafer. For step 19, which is the formation of terminals, in the gaps left after removing the excess metal, we form terminals for the interconnection. And finally, for assigning terminal names, and last but not least, we give names for these terminals for our NMOS and PMOS transistors. Think of it like labeling all the connections on a complex map. That's all from me. Thank you.